Hi, I'm Eduardo Serna. I work in the probability statistics group at Wolfram as a consultant. I imagine most of you attending this talk just came from my colleague's talk, which I couldn't attend all of it because I was getting ready for this one. But I know the content, and hopefully means that I don't have to introduce every concept. I'm going to be talking about the model side of this spatial statistics new framework that we're finally releasing after a lot of work. Some of you might have attended previous talk on this. This time it's coming out. So I'm just gonna give an overview of the process side of things. Gosia was talking mostly about data, or she also mentioned processes a little bit. So first of all, I just want to motivate why we want to deal not just with data, but with processes. And processes allow us to really make inferences about the real world, an unseen population, or the underlying mechanism that is causing a phenomenon. And spatial point processes allow us to model an increasingly pervasive array of geospatial data, human activity, natural resources, epidemiology, ad tech, stuff like that. This is stuff that is becoming very important nowadays, and very big data sets are coming online. People are very interested in this. And we have, for now, focused on three types. There's different types of families of models. We have, for this iteration of the framework, we've focused on three types of models. Poisson models, which are the simplest ones, where points are independent from each other. We also have pairwise interacting processes called Gibbs processes. And these are the simplest type of processes where points are not independent of each other. And we also have a different type of non-independent process called cluster processes. And although they're technically a subset of interacting processes, but these are not necessarily pairwise. And here, in these type of processes, points are generated around seeds that then generate a cluster. I'm going to talk about all of these three families, giving examples with data and trying to show some toy applications. So the Poisson processes, the Poisson family of processes, we have three processes implemented. The Poisson point process, which is the simplest one, a canonical one. We have a constant point density. All of these processes generate a collection of points where the number might not be fixed. And this is true for all of them except for the binomial point process, which is the only one that has a fixed number of points and generates what is in the system the equivalent of random point or random geolocation. All of the rest generate a variable number of points with variable distribution. The second simplest, in some sense, is the inhomogeneous Poisson point process, and this one has a density that might vary from point to point. And although it's very simple because points are still independent from each other, it's very general. It allows us to represent loads of different types of data. I'm just going to move on because I'm running out of time. Okay. Let me check the chat 1 second. Okay, good. So Poisson point process is the simplest process. Points are uniformly distributed over the observation region. They're independent from each other. And this last condition requires that the number of points, in fact, is not fixed, and furthermore, Poisson distributed. It is defined by its density lambda, which is the mean number of points per unit measure. To sample from a point, from a process, when we specify a region, And we have been putting a lot of work into making sure that the integration with the geographic framework is as good as possible and as fast as possible. So and these are the most interesting examples. I'm gonna show an example from my home region, which is Madrid. So we specify the region, we specify the density by giving the number of points that we, on average, we want to have divided by the measure of the region. And so the density will be 0.0112 points per square kilometer. And now we can sample from the region. And the sample has 106 points, which is not 100 because 100 will be the average. This number is Poisson distributed. And we can see that they're all within the region of Madrid. So let me move on to the next slide. Let's use it to model real world data. Let's look at the towns in Madrid. And we can see what the largest towns are by population, which happens to also be now the ranking of COVID cases in the whole of Spain right now, disastrously. So we can see that we have 182 towns in Madrid, individual towns. We create this spatial point data region, the spatial point data structure by giving it the points and the region. Otherwise, as Jose was talking about, we will generate I'm not muted, right? This is okay. I'm seeing a weird thingy there. We will see we will generate the Ripley-Rasson observation region, which is the dilation of the convex hull. So this is a plot of the actual towns in Madrid, and we see that there's like a big gap around the center of Madrid because it's the big town, the capital, and there are also gaps where we have parks and stuff. And one thing we can do is this: can we conclude that this is reasonably spatially uniform? So we can. This is something Gosia showed as well. We can apply spatial randomness test to the town location. So we ask for the p-value in the test conclusion, and the p-value is small, but well, it's much bigger than 0. So at this confidence level, we can say that this data could be random. We know it not to be, but it could be, at least using the chi-square test. We can also estimate the parameters of the process. And for this we get a density that is 0.2. The estimated density here is 0.02 points per square kilometer. And using this estimated process, we could ask: is it reasonable to conclude that it's actually generated by this process? And this is something that I'm going to evaluate because I want to show this is something we've been putting some work into. I hope it works. So, and this is not fully in. There's still more functionality where we wanna add these user interfaces, but I'm gonna do a small number. I just wanted people to show that there is some feedback. A lot of the functionality here is using Monte Carlo methods, numerical methods, and there's some feedback to the user of the things that are gonna take some time. And this would be like, this test would be too conservative because we're using a process that we previously estimated from the data, but it's more of a sanity check, and I just wanted to show the user interface. Let me talk about the inhomogeneous Poisson point process now. it's basically the same as the Poisson process, but the density isn't homogeneous, as it says in the name, and it's varying from point to point. And this is a very general process and allows to represent process non-parametrically. So we can do the Voronoi point density that Gossi has shown earlier, and we can use this Voronoi point density, which gives us a point density function, to sample from an inhomogeneous Poisson point process, and this will give us a realization of this process that has this non-constant, this non-uniform density. And we can see here that this is both the data and the sample have gaps and are more dense in the same places, which is reassuring. Okay. We can also use we can also use just any non-negative function as a point density. This didn't happen. Okay. So for instance, this exponential, I'm going to use an extreme function to show that we can, when we sample from this, we'll get like a very skewed distribution that is heavily weighted towards the top here and slightly to the right. So here I'm showing the contour diagrams of the density and the sampled points in this region. There's loads of points at the top, almost no points at the bottom. Okay, let's move on. Okay, now we get to the more interesting process. I'm first going to talk about the pair-interacting Gibbs processes. These have a pairwise repulsive interaction. Repulsive because if they were attractive, they wouldn't be stable. They would just keep generating more and more points. We have a general Gibbs process called Gibbs point process, which is a very general object, which is the equivalent of the inhomogeneous Poisson point process. And it takes a general density in pair interaction and will generate an arbitrary Gibbs point process. The issue is that it's less optimized than the common. We have also implemented the common Gibbs processes, which are more optimized. And you can do estimation and sampling much faster than for the Gibbs point process. So an easy way to characterize these interacting processes are by looking at the pair potential. The pair potential describes the radial interaction between 2 points closer than a radius. When a value of 0 means that there's no interaction, so that's the effectively interacting radius, and infinity means that you can't have any points closer than that. So for the hardcore point process, this is exactly what we see. But then we have other softer core point processes like the Strauss point process, which is the canonical soft core interacting process, a mixture of both the Strauss hardcore point process, and then other more subtle interactions that might be useful in different cases, like the Pentinen, Diggle-Graton, and Diggle-Gates point processes. Let's look at one of the simplest interacting point processes, the hardcore point process. Here, points are distributed uniformly with density lambda, but they're not allowed to be closer than radius r of each other, as I was saying before. An example I looked at from real-world data is pharmacies in Madrid that are not legally allowed to be closer than 150 meters walking distance. Just looking at pharmacies closer to my home, this data I got from a government website. You can see points, these points represent the pharmacies. And it's always useful to see, could this be just a Poisson process? And in this case, again, we see that it is. But still, we know that we have prior knowledge that suggests that actually a hardcore point process is a better fit for the data, and it will give us more information about the underlying mechanism. the fact that in fact they're not allowed to be closer than a certain distance. So we can estimate the process, and this will give us the density and the minimum hardcore radius, which we can convert to units in my own country. 50 meters, 43 meters. This is the difference is partly due to the fact that some of them might not follow the law. This is not that rare in Spain, and some of them we're actually looking at distances, geometric distances as the crow flies, as opposed to walking distance. Okay, let me skip this one and this slide. Let's talk about another process which is a little bit more interesting, which is the Strauss point process, which has a soft core. And let's look again at the towns in Madrid I showed earlier, and it's say that it's reasonable that we can model the distribution of towns by saying that towns are likely not to be too close to each other, because otherwise they would just become a new town that is a bit bigger. One of them would eat the other town. The simplest model for this kind of soft core repulsion is the Strauss model, which has a constant penalty for towns being closer than a radius r. So we can estimate the data, and this is something that I want to run to show the interface as well. It's pre-computing some data to start the estimate, and now we'll start the estimation. And again, we have this nice user interface, and oh, that was too quick. But it's trying to minimize the pseudo-log likelihood, and it gives us these parameters. We can see that it's estimated, even though the mean point density is 0.022, it's estimated slightly higher density as a parameter, but then there's this repulsive interaction that actually lowers the number of points. And it tells us that there's actually the Strauss radius is, the interaction radius is 2 kilometers, approximately 2 kilometers. And we can see this in this visualization, where we see that most of the towns are in fact outside of this radius, but some of them are closer, and there are these overlaps. And they're allowed to be closer, just there's a penalty for it. Okay, I need to be quick. Okay, I'm almost done. So let me talk about the general Gibbs point process, which is, as I said earlier, a further generalization of the inhomogeneous Poisson point process. And it takes an arbitrary point density and a pairwise interaction. And this pairwise, there's also, you can also take a general interaction density, and there's actually several different ways of specifying the interaction that I'm not going to talk about now. For instance, let's just give the pair potential of the hardcore point process, but instead of a constant, the constant density hardcore point process, we're going to give it a varying density. So let's simulate a hardcore point process where the and this is the pair potential of a hardcore point process. It's infinity if it's smaller than the pair potential is infinity if it's smaller than a radius. And let's just use a density that again is exponentially increasing, so that they're biased towards one end of the observation region. We can generate the points, and we can see that what generates the points, and this is the picture we have. There's no points that are closer than the hardcore radius, essentially, and there's all of them are to one corner of the observation region. Just to show that this, we can also compute the point density again of this sample using, for instance, the Voronoi density, and we can use this as we could use this to generate the the new data. And this would be less exact, but because what I'm saying is that Gibbs point process also takes non-parametric densities because this just behaves like any other function. So we can give it to the sampler and it will generate the data. And because this is piecewise constant, the sampling is actually a little bit faster. In this case, it took 6 seconds earlier. Now it takes 2 seconds. Okay, I should wrap up. Okay, the third family that we have of point processors are the cluster processors. Here, clusters whose centers themselves from a point process are used to generate a point process around each center. We have the general Neyman Scott point process, which is a general Poisson cluster process, where both the seeds themselves and the number of points in the clusters are Poisson distributed. And we also have implemented a family of common Neyman Scott processes like we did with the Gibbs. And these can be understood by looking at the radial distribution. They differ in the radial distribution. So we have the Martin point process, which has uniform radial distribution. So they're uniform inside a circle around each seed. The Thomas point process is normally distributed radially. Cauchy point process has a heavy tail, the Cauchy distribution. So the points can be much further away from the center. And we also have the variance gamma point process, which has a normal and gamma mixture for the radial distribution. Okay, so let's look at an example right before I finish of the Thomas. Wait, let me look at chat. Okay. Okay.
Yes, Eduardo, you have some chat in Zoom.
Yes, I will upload the notebook. I'm gonna upload the notebook. Yeah, I will. I've been making changes to it the last second, so that's why I haven't done it yet. But I will after the talk. So yeah, I just finished with an application. The cluster point process can be used to model epidemiological processes, like, for instance, COVID spread. The Thomas point process I'm going to use here. We're going to use it to model the cough droplet distribution around the population of infected people. So, and this is because the radial distribution is normal, which is reasonable to assume that there's more cough droplets closer to the person that is infected than further away. So we can specify the parameters like this. I'm going to assume that we have a room that's 10 meters by 10 meters, and I have only one infected person that is one of these super contagious people. And let's assume they give away 1,000 cough droplets per infected person. And the reach of these droplets is 2 meters, which is the distance that they're always telling us to stay away from each other. So we can sample this, and we can see that each time we sample from this process, we'll get a different distribution of, and sometimes it will be, sometimes it will be, they will be in the center. Sometimes there will be more than one person. It depends. And we can compute with this. We can compute the mean point density of the cough droplets. In this case, 10. And here the question is like, is this a big number? I don't know, because I'm not an epidemiologist, but this is a tool that can allow an epidemiologist to figure out if this is a number where someone is likely to get infected or not. We can also use one of the second order statistics that we have to look at this will give us the probability. Empty space F will give us the probability that we have that we're in contact at radius r to at least one of these cough droplets. And we can see that and this is for the whole room. And we can see that above a very small radius, above a few, like a quarter of a meter, we're likely to be, really above a half a meter, we're very, very likely to come into contact with one of these cough droplets. So being in a closed room is bad news, it seems, for COVID. Okay. I think this is the end of my talk. This is functionality that is coming with 12.2. Finally, we have been leveraging all the geographic and geometric functionality in Wolfram Language to implement all of this and integrate it. We've put a lot of work into optimizing different cases, implemented different data structures to make sure that all of these computations are as fast as possible. And we hope that people like it and enjoy it. I'm going to finish now. Okay, questions?
I think, Eduardo, those were only sent for us to see, so you might want to read the question before you answer it, because I don't think all the Zoom members can see the questions.
Okay, I'm seeing the ones in the chat, right?
In the webinar chat,
Yeah, okay. So Jose is saying, any good reference for getting started with spatial statistics, especially with Mathematica? Well, this is stuff that we're just releasing. So hopefully our documentation, we're striving it to be the place for it when it comes out. Yeah, but there are some good books out there as well. I can send you reference. I don't know. I don't remember the name of the books, but Barley has done a lot of work on this. And then let me see. Can you load the video? Okay. That's it. That's the only question. Okay. The reference in the file, in the notebook. Okay, I'll add the references in the notebook, I guess. Okay. Great. Okay. Thank you all for attending my talk. I hope it was interesting. Bye. There's another question. Wait, there's another question in the chat by Seth Chandra.
Yes, sorry.
Okay.
So
Yeah. In the Zoom
go to the
chat.
Zoom menus, go to chat. There's a couple
okay.
there.
So Seth, yes, the p-value test was a problem. The population itself isn't it takes population density into account. Well, I think the p-value test that I did in my talk was a problem because I had estimated the process from the data itself and then tested for it, and that is so that will give me a better result than if I hadn't made a correction. Our probability framework corrects for this, but this is like an open research problem, and it's in fact very, very hard this is still an open problem, and people don't know how to do this yet. So this test is only really works if you already know the process that you're testing against. Nevertheless, as with all p-value tests, it really helps you to reject data categorically more. I think it's useful if you get a very small p-value, you know that the data is not distributed according to the process. But if you get a p-value that's not that small, is nothing. You can't really say anything about the fit. Okay, let me continue reading. Is the clarify suppose? Okay, so what you're talking about with the Nile River Delta, well, one of the ways to do this would be to have the observation region like a narrow strip along the river, and that would in fact take care of that. Another way of doing this is with something that's called covariates, which is something that we haven't it's not coming out in this release of the functionality, but there's a way to basically correlate with data that is extrinsic to the point pattern itself, to the point collection itself. Has Has this been applied to cosmological data? Yeah, this is one of the fields where this all comes from, actually. Like the cluster processes are, Strauss was a cosmologist or something like that. So yes. Yeah, covariates for version 13. Yeah, hopefully. I don't wanna commit to a number, but yeah. Okay. Other. Okay. I think this is all. Okay. Thank you again, guys. Take care.